So you probably know from yesterday, Michael Hava is one of the representatives of the Austrian national body in the ISO C++ committee. He has been here before. He's the third year you are here. So thank you, Mike, for coming. And he's going to talk about reflection. And you might say, okay, but reflection will be in C++ 26. Probably it will be 5 to 6 years before I can use it. And the answer to that is no. What he's going to talk is how or what can you do today. And I'm pretty sure that it's going to be a lot of fun.
Yeah, I expect so as well.
So thank you very much, Mike, for coming.
My pleasure.
The floor is yours.
Okay, talking about reflection. What is reflection? Let's start with the easy stuff. So for me, reflection is actually two features in a trench coat. So there's introspection, which allows you to actually examine what's going on in your application. And there are some languages that only support introspection. And the second feature is intercession, which allows you to actually modify your program. And we can discuss how far that modification goes. In theory, there could be a way to rewrite the code that you've written. We are not going to look into that. We are going to look into a more limited way of intercession. And this is a feature of many modern programming languages, and I should put the modern into quotes because all these languages are pretty old now. Go isn't that old, but Java and C# are old. And I never really got to like these languages, but every time I had to use reflection, it was like, this is so cool. Why can't we use this in C++? And what are these cool use cases? Well, we can easily do serialization with this. We can do command line argument parsing without actually having to do all the nitty-gritty stuff every time. We can do OR mapping, which is a great hassle if you have to do it by hand. Or in a more general case, we can actually do code generation. And yeah, so code generation is obviously something we are all interested in. And if you think about it, C++ doesn't have reflection right now. But if you actually look at the features the language has, there's some support for introspection, some support for intercession already. So at runtime, we have one introspection feature, which is RTTI. And I guess everyone in the room will agree that RTTI is pretty useless. But we have a whole lot of compile time introspection features already. Like we can use type traits, we can use template meter programming, and who doesn't love template meter programming? And thanks to C++ 20, we can actually do that in a readable manner with concepts and requires clauses. And we have intercession features already in the form of template meter programming and compile time function invocation. And the most daring of us will probably know that there's something called preprocessor meter programming. And yeah, we've talked about the preprocessor yesterday, so I'm not going to open that can of worms now. So normally I have a rule, I don't talk about features that aren't in the standard now. And reflection isn't in the standard right now. Our next meeting will be in summer, and I have high hopes that we will get it. Otherwise, I wouldn't present this. So we will get this feature, which we call reflection, and let's walk through what actually goes on here right now. So what you should know is everything related to reflection happens in the new subname space meter. And in there you will, and we get a new language feature called template fort. It's a so-called expansion statements, and compiler writers have multiple times explained to me, this is not a loop because it's expanded at compile time. I don't care, this is a loop that runs at compile time. And what we are gonna loop over will have the type info because everything in reflection will have the type info. And the best way to think about info is it's a type-erased handle into the AST of your compiler. And you can only examine this at compile time for obvious reasons, and then it's gone. And what we're actually getting, where does info come from? Well, we have this funny looking operator. We don't have a nice name right now, like spaceship or something like that. We'll probably have to figure something out. Eyebrow. Yeah, okay, that could work. Yeah. So this is the reflection operator, and it returns you an info, and you can apply this to a type and pretty much anything. And what it will yield is an info object, and this info handle has no operations. Everything's done with functions in the meter namespace. And the first one we're going to use here is non-static data members of, which gives us a vector of info objects for all the members in this thing. And for some complicated technical reasons, how allocations at compile time currently work in the language, we can't actually loop over this thing here. But we can allocate a static array, initialize this with a copy of the content of that vector, and through some magic that works. So we can loop over this, and I hope we can get rid of that in 29. But getting everything else into 26 and figuring out how to get rid of this stuff, that's way better than delaying this feature till 29, right? And what this does is now it's gonna call printline, and we're gonna print a simple string where we get the identifier of, which yields a string with the name of the member we just got. And with this funky syntax, the so-called splice, we're gonna inject an access to the respective member into the code. So if we call this function with a template, with some class, it will yield this output. And I think that's pretty cool. Like, yes, I want this, and I want this now. But as Daniel already alluded to, this is for 26. So let's make a little experiment. Who here is actually writing 23 code right now? We are not many. Who is writing 20 code? A few more hands. 17. Ooh. Okay. 14. And feel sorry. I don't want to go further on because then I'd have to ask for an ND8 and I really don't want to ask the question. So this is cool, but I want this now. I don't want to wait 3 years because the 3 years won't probably be enough for all of you to get this. And what we're going to focus on for the rest of this talk is some subset of reflection we can get right now in your compiler. My slides will contain code that's mostly 20 and 23 code. We can probably get you to 17. Maybe even 14, I haven't tried. So, how can we do reflection right now? I mean, there's the obvious answer of, okay, I'll do my own preprocessor and generate all the meta information I need. You can also have your custom file where you generate all these things, not from a C++ code, but from some external definition. A friend of mine works at a company where they have a JSON description of their types and generate C++ code out of that and get all this meta information in addition. If you want to stay inside the boundaries of the language and you don't want to do a whole lot of template-y things, probably one of the best things you can do is something like this macro, where you enumerate all the members. And yes, this is fragile, but this enables you to do easier generic programming than do it any other way in the way the language currently works. So what will this macro actually do? It will generate something like this. But we will have some way to represent our member type. And it will have a reference to the actual instance and a string literal with the name of this instance. And, well, we'll just return a tuple because you'll see that tuples are everywhere. Because tuples are like the only compile time heterogeneous container we can currently use, especially when it comes to intercession. And, yeah, that's one way, and obviously this tuple can be generated with a little bit of preprocessor magic. So, what we're gonna do with intercession and tuples. So, for all of you who haven't done anything like this before, this is probably a reaction right now. Like, what is going on? So, as it's the only tool in NoAF we can use, let's step through this, what's actually happening here. And let's act like a compiler and do this by calling this thing with our test class. So the first thing we notice is we are calling a template. So is this a class? Yes. So let's generate the template instantiation. Okay, that wasn't too hard, but we're not done yet. What is auto members? Well, we need to deduce the type of that. So that's some unspeakable tuple type. And we need the tuple type once again as members. And then we see that members is actually used right there as an argument for tuple size. So obviously we can just put that in there, and tuple size of a tuple with 3 members yields us the size tier 3. Oh, the code just got way easier. Okay, still complicated, especially the next part, which looks like a lambda, but there's a whole lot of stuff going on. Let's jump to the call set, because as you see, it's an immediately invoked lambda. And see the size again. And we know what size is, so let's handle that one first. So there's a 3. And what is make index function? Make index sequence. Make index sequence is a factory for an index sequence from 0 up to excluded 3. Okay, this still looks quite complicated, right? But let me highlight something. We have this templated lambda thingy, and its template clause is a pack of values. And our argument list takes an index sequence with this pack of values. And we are calling this with an index sequence with 3 values. Or in other words, what this really complicated stuff actually does is the pack of values is this. And the funny thing is, this is the simplest way to do this in C++, because packs must be deduced, and you can't just say, hey, this is my pack with these 3 values. There may be something in a future version, but in 23, this is the best we can get. Okay, now this looks way simpler. Let's look at these 3 dots there. That's a fold. And what this, roughly speaking, does is it replicates the statement to the left for every value in our pack. Or in other words, it just generates all these statements. Now we have a simple, immediately invoked lambda without any context, so let's get rid of that stuff. And we can simplify a bit again, because there's a comma in there that nobody needs. And all of a sudden we have a function that prints our members exactly like the reflection version we just had. And that's great. Like, that's really great to have shipped programs with this, because this is way better than having to write the print function for every type. And especially if you come to OR mapping, etc., seeing how you can automate this instead of having to write it every time again is really mind-blowing how much code you can save. But is this really great? Yeah, it's great, right? But it's not good enough. Like, as I said, I've shipped programs like that, and I thought this is the best we can do, but as it turns out, no. We found ways to be even better. And I'm gonna set the mission statement for the rest of the talk. Like, I want this code to work. We will have a generic print function, and we'll not look at the implementation of that one right now. And then I want to have a type that's not annotated in any way. I don't want to be any external annotations either. So no template, specialization trickery in the background. And I want this function to not only compile, but this should be the output. And we're gonna do this in 4 simple steps. Step 1, we're gonna figure out how to make this test class a tuple. Because as we've seen, we need tuples for intercession. And we're gonna need references to the members so we can later on get the values of those members. Then will come the really fun part. figuring out how to get the name of these members, even though, according to the standard, everybody will tell you that's not possible. Then we'll build this up into a nice user interface in the form of a tuple of member objects. And later on, we'll just implement the print. So that's the plan. Let's just start with step 1. How can we convert a class into a tuple? And the first thing we need to know is this won't work for any kind of class. Actually, the set of limitations we need our class to have is pretty big. And what we're going to need is something at in simple aggregate. And the simple aggregate looks something like this. At this point in my talk, there's mostly two kinds of people. The ones who go, okay, nothing here matters anymore. If that's the limitation, I can't use this. My classes are way more complicated. And the other group of people is like, yeah, 99% of my classes already look kind of like this, so that's not a big deal. So this talk is only for the second group. So what's a simple aggregate? Well, first of all, what's an aggregate? Thankfully, the rules for what an aggregate actually is constantly change. So in 23, the rules for an aggregate are broadly. All members of the class are public. This thing has no private, protected, or virtual base class. It may have a public base class since 17. This thing may not have virtual member functions. Oh yeah, and it may not have any constructors. So yeah, no user-defined constructors. Obviously, this thing has a whole lot of automatically generated constructors. Yeah, okay, user declared. There's a wordsmith over there. So, but that's not enough. We can't do it for aggregates. We can only do it for simple aggregates. We need 2 additional rules. All our members must be default constructible. And this thing may not have a base class. So we need this as verbatim here, not as the standard would say it's an aggregate. Okay, that's a whole lot of limitations. What does this actually give us? Well, simple aggregates have 2 interesting features. One of them is structured binding, where if you know the amount of members this thing has, you can get a reference to every member. Note that if you say you have more binding names or less binding names than this thing has members, it will not compile. And there's no way to query that in C++, you just have to know, which is obviously great for generic programming. So that's one of the features we're going to use. The second feature is these things have really interesting initialization rules. So if you use braced initialization, and you should always use braced initialization and you don't have uninitialized data members, then all of these statements are equivalent. Because whether you provide the curly braces or not, it will call the default constructor and do value initialization. So, okay, these 2 rules. And funnily, these 2 rules will be enough to implement this tuple. Because let's express a simple aggregate as a concept. Obviously, it's an aggregate. It itself must be default constructible, which nicely checks that its members are default constructible. And it has no base class. And we're gonna delay talking about how to prove that this thing has no base class to the bonus slides if we don't run out of time. If we do run out of time, come to me in the break and I'll explain it. So, and then we're gonna add another concept, aggregate 0, which is a simple aggregate with 0 members. And this thing will obviously be a simple aggregate, and it must support the initialization syntax with empty curly braces. And up on top of that, we'll build aggregate 1, which is an aggregate 0. And in addition, it requires us to be valid to be initialized with 1 curly brace. And so on and so on. So, given these concepts, a short reminder how concepts can be used. You can use concept as a predicate for a type, and it will yield you true if this thing implements everything the concept requires, and otherwise yield false. So all these asserts hold. That's not really the use case for concepts, but it's nice that you can do that. But actually, the use case of concepts would be something like overloading based on these concepts. So we have all these overloaded functions, and you take the different concepts. And if the compiler encounters a call to this overload set, it must do a simple task. It must determine what is the most concrete concept we are actually implementing. In our case, that's aggregate 3. And it must call that one. That's pretty much how subsumption works. That's also how overloading based on inheritance would work. As a hint how you would do that in C++17 or before. Okay, so we can just now write an tuple function. And obviously we're gonna need a whole lot of overloads. And what we're gonna do is, if this thing is an aggregate 0, it had no members, so we'll just yield an empty tuple. And if it has one member, well, we're gonna use structure binding to get a reference to the first member. And then we're gonna call std_tie with that one member reference, and std_tie yields a tuple of references. So we got a reference to our object through val, we got all the reference to its members, and we package those up in a tuple and send this back out to the user. Okay, and we'll just replicate that logic for all of our concepts. And now we are done. This is working code. And in a real implementation, you probably need const overloads as well, but yeah, there's only so much space on a slide. Okay, now the really fun part. How do we get the name of a member? First, some bookkeeping. We're gonna need a compile time string, and this is a completely trivial case. We have a class with some character buffer internally. I'm not even bothering to do null termination because what gives? And this thing can only be constructed in compile time. It will be available at runtime because there's no dynamic allocation in this, so it's no problem to move this to runtime later on. And we have one operation which is a conversion to string view because we don't want to replicate the interface of string. Have you looked at this thing? And we have a formatter because otherwise println wouldn't work. Okay, but now, how do we get the name of anything in C++? And the answer is you can't. There's only one thing you can't get the name of. Does anyone know it? Any idea? Yeah?
Pretty function?
No. Then we can get the name of a function. And we inherited this feature from C99, where we have this underscore function, a func thing that gives us a stringlet with the name of the function, which is super useful apparently in C, but is pretty useless in C++ because we have overloading and the name of a function doesn't tell you anything. So if you have a C API on your DLL or something, you can do logging based on this thing because that would be unique, but other than that, I've never found a convincing use case for this thing in C++. But yeah, and we'll just catch that one in a string view at compile time so we can get the size of this thing to allocate the right amount of buffer, then initialize the string view, the fixed string. So, as I said, completely useless for any amount of code realistically in C++. But, yeah, pretty function. The compiler writers are so nice and provide us a more complex view on how this thing is called. And in GCC and Clang, it's called pretty function. Microsoft, it's called funcsig, and the strings it yields are roughly similar in terms of the information they contain, though the actual format of it is compiler specific. We are only gonna use the GCC outputs here because, the code will work for everything, but you need to adjust to the respective format. So, okay, as you can see, this thing now includes the return type. It also adds the const eval thing. And if we had parameters, it would also yield the parameter types of this thing. Still no way to get the name of anything other than a function, right? Well, as it turns out, we have templates. And if you make this thing a template, what do you think is going to happen? Well, the string this thing is going to yield tells us what was the template argument you called me with. And I have no idea who first figured this out, but a certain part of the C++ community, those crazy people who also do template media programming, were like, oh, this is a new feature. What else can we get here? Is there anything of value you can extract here? And as it turns out, we don't only have templates that take types, we also have templates that take values, right? So with a little change, we'll take a value, some value that is available compiled. For example, an integer. And this thing will tell us, yeah, that's your integer. So, okay. What else could we put in there? Well, as it turns out, we can do member pointers in C++. And if you put in the pointer to a member, this thing will tell you, yeah, that was the pointer to your member. So, okay, there's the thing we want, there's the X. Only one problem, we can't get that X. There's no way to generate all the member pointers from a class in C++. But is there maybe another way to reference this X variable? Well, we could construct a test object, convert it into a tuple, get the first element of this thing, get the address from the reference. You see where I'm going? And the compiler will be, no. That's not the address of a variable. That's one of those super helpful compiler error messages where there's obviously a variable there, but my interpretation is something like, this test thing is constructed on the fly, so it will be constructed at any point in your memory, and then later on you will get a pointer to there. So if you do this again, it would be a different address, so that's like preventing us to violate ODR. And if that's a correct interpretation of the issue at hand, well, I'll just give this thing an object, because I can totally do that. I can say, hey, here's your inline variable. That's always going to be at the same address after linking. And who thinks this works? Obviously, this looks correct. There's a bug, though. The instance isn't initialized. Remember when I told you should use braced initialization? Yeah, but we can just add braced initialization there, right? And now the compiler will gladly say to us, yeah, sure. There's an object there. And by the way, this is the pointer to its member. So in theory, we are done now. We can now pass this string here and be done. There's one problem. We need to construct a const export instance. And for string this works, but say you have your map or a list inside your aggregate, then this won't work because those are not constructible at compile time. So, okay, this would be a severe limitation. We could live with that if we can't figure out a way to do this for any type. But as it turns out, we can do this for any type because there's another magic word, it's not inline. It's called extern. We can just say to the compiler, you know, there's this external object somewhere. Trust me on that one. I'm not constructing it here, but there's somewhere this object. And if you do linking, it will always be the same object, so the address is stable. And obviously, we're not going to provide an instance because we only need this at compile time. And the compiler will gladly give us the name of this member again. And once we have this string, all we have to do is a little bit of string processing, like remove something from the front and from the back. Obviously, this is the part where you need to know how your compiler actually generates this string. But yeah, now we have a way to get the name of a member. And yeah. And the first time you figure this out on your own, you're like, my God, what have I done? Obviously, I wasn't the first, but I had to figure this out on my own because that's just the way I learn stuff. So, okay, we have that one. That's step 2 done. Step 3. Step 3 is easy. We'll define a template for our member, and it will take 2 parameters, the type and the index. So it's representing the ith element of this class. And we're gonna need some way to access this thing nicely, so that's an access function that gets us the respective member of an instance. And obviously we're gonna cache the name now that we have it. And now we're gonna put this in a super user-friendly API, which is a type alias to a tuple type of all the members of these things. And I'm probably the only one in the room who thinks that's a nice user API. Wouldn't it be nicer to have something like a for each member API? Sure, that's just using that one, and I'm only dealing with the low-level parts here. And that's step 3. We have our user-friendly API for some definition of user-friendly. Now we can implement print. And this will actually be super easy now. We are in the template and we just get the members. And we're gonna construct an instance of the tuple because that's the only tuple API that will fit on a slide. You could do it with the tuple element thingy, but that gets way too long. And well, then obviously we're gonna use some intercession, and we all know that this is gonna work. And what we're gonna do is we have a print function that gets the name and the reference to the respective member. And this thing prints the correct thing, so we've just done it. We've implemented our print function without any annotations on our test class. So this works. Obviously, there are probably questions about, wait, isn't this gonna break the moment I'm gonna deploy it? And there's this funny little thing called Hiram's law, which says it actually, if you have enough users, it doesn't really matter what you say in your API, because every change to an observable effect will be a breaking change. And given that there are popular libraries that depend on this thing, like Magic Enum. Who has heard about Magic Enum before? Oh, a few, okay. And there's Boost.PFR, which does pretty much what I'm doing here with a user-friendly API for the normal people. My implementation is here. It also deals with enumerators, and you can extract the scopes and the type names, though those get really complicated pretty fast once we are talking about templates. Because what's the name of a type in C++ if you're talking about dependent types? And yeah, there's questions. Daniel, before you start questions, how am I doing on time? How am I doing on time?
You have a lot of time.
Okay, then do you want to know more? I have a few. Yeah. Really?
Coffee break is like 11:10.
There may be a whole lot of questions after the next few things.
Okay, so you can do more.
Yeah, I have a few bonus slides.
Okay, bonus slides.
So, remember when I said has no base? And to actually figure out how to prove that an aggregate has no base, we're gonna have to think about what actually happens with aggregates that have bases. And the one thing that changes is you can't actually provide a braced initializer for every member, because the first braced initializer will be the initialization of your base class, irrespective of how many members that one actually has. So we can only provide up to 2 braced initializers here, although we have 3 members in derived. So that's not supported. Funnily enough, if you use real values and not braced initializers, this actually works. And why does this work? Because the first braced initializer is the initializer for your base class. Or in other words, aggregates allow construction of a derived object from its base object by value. That's not something that normally works in C++. That's the inverse of slicing. I don't think we even have a name for that kind of thing. So what does this mean? So let's say we have a helper, and the helper tells us whether we're going to have a base class by providing us a conversion function. And we have one requirement: the conversion function must convert to a base class, and it must be a real base class, not the same type, because is base of is kind of wrong. If you say is base class of t and t, it will say true. Don't know why. Yeah, and now this one is tricky. So let's read that one from inside out. So we want to construct a t from a base aggregate of t. So if this thing has a base class, it will be able to convert to its base class, which means the syntax for the requires clause is valid, which means this thing has no base. Because if this thing has no base, then the syntax in the requires clause is invalid. If it's invalid, this means this thing fulfills it has no base. Don't want to know how long it took me to figure that one out on my own. Yeah. The elephant in the room. This only works for a limited amount of S-tuple overloads, right? And what is the correct amount? I mean, we can discuss how many function parameters a thing can get, but would we like to discuss how many members a class can get? And do we want our library to have this hard limit by the virtue of not providing more overloads? Or do we want the user to be able to decide on what's the correct amount there? And just as a reminder, our code looks something like this. Like we have this base case with the empty version, and then we have a whole lot of concepts that say, okay, it's the preceding one, and so on. All this looks very mechanical. And we could obviously generate all of these things, for example, with some scripting language. But I don't want to have any dependencies outside of C++. So is there any way to do this with template metaprogramming? What do you think? Is there any way to generate all these overloads with template metaprogramming? Parameter packs sound like a nice idea. One problem, there's one key limitation to templates. We can't generate new identifiers. So this _0 thing, you can't programmatically generate this thing in templates because templates don't work that way. Thankfully, we have another way to do metaprogramming, right? All this talk about the preprocessor being abandoned. Yeah. Not gonna happen. Though we're not gonna use the preprocessor verbatim because that messes with my brain. And for someone who does template metaprogramming on a regular basis, telling you that should give you a warning. So we're gonna use Boost preprocessor, which is a user-friendly API to do preprocessor metaprogramming. And I've grayed out all the parts we don't actually need. So let's define our metaprogram. Our meter program now obviously has to be a macro. Let's call it as tuple. And it's gonna get 3 parameters by the designer of Boost preprocessor. We're only gonna need the second one, which is the index of the loop we're gonna execute this thing in. So as tuple will be called in a loop, and n is the runtime index of this thing running in the compiler. And what we're gonna do is we say, okay, we have a new concept. It's aggregate underscore n, concatenated as you do in the preprocessor. Because that's the superpower of the preprocessor. We can just generate new names. And this thing is aggregate n minus 1. And sure, we need to replicate this requires clause, which requires us to enumerate. And enumerate yields a comma-separated list where every element of the list is initialized with the function you give it, which in our case is only a braced initializer. And after that one, we obviously need the tuple function. And that one's gonna take our new concept we just created. And then we're gonna do a structure binding where we enumerate. And this time enumerate will just concatenate underscore in front of the runtime index. So we have a unique identifier. And yeah, in Thai we do exactly the same. And now we have our working as tuple implementation. And yeah, we need to actually execute this program. So that's a for loop that starts with 1 and exclusive 11 calls as tuple. And for a real implementation, you would obviously move this 11 out to a user-defined macro constant. But now you can configure how many overloads you actually support here. Yeah, one last thing, because last night I noticed a whole lot of people were happier about why can't you provide us a function that gives us all the names of the enumerators of an enum? We're not going to go through this in detail. I thought it would take longer to get here. So obviously it works on the same principle. If you instantiate this thing with an enumerator, it will tell you, hey, that was your enumerator. But just as you can't get the names of all your members, you can't get the names of all your enumerators in C++. But thankfully, if you cast integer to your enum value, it will actually tell you that's the enum value. The question is, what happens now? You think, ouch? Well, this obviously is going to compile, right? Because we don't do checking whether an integer is in the range of valid enumerators. The question is, what does the compiler tell us? Well, it just tells us, well, that's the name, value 5 in this enumeration. And this hints at why libraries like Magic Enum tell you, you know, there's an upper bound of how many enumerators we can support. Because from an enumeration, you can't get the range of valid enumerators as well. So the only way to do is exhaustive testing. Exhaustive testing, all possible short values works. If you try this at compile time for all integer values, you probably get a compile time error because you ran out of memory in the compiler. And yeah, so that's just horrible, but that's pretty much how Magic Function actually, Magic Enum actually does that. And if you want to have, I think it's like 100 lines of code, you can look at my implementation, which is very bare bones, but I think is very instructive compared to some real-life code base like Magic Enum, how to actually do this kind of magic there. I'm now really out of slides.
Okay, thank you very much. Questions?
Well, I'm gonna tell you that I've deployed this in production. Just like I've deployed the other stuff before.
Does this also work recursively when we have a struct inside of a struct?
Yeah, sure. Not automatically, obviously. But you could obviously say, in my member, I'm now gonna check, is this a simple aggregate again, and then go one level deeper. And you don't need the preprocessor for that one. That's just recursive templates now. But yeah, I've not done it recently, but sure.
Not so much a question, but a comment. With C++ 26, you actually can use auto angle bracket.
I know,
dot,
but you know,
equals.
if your compiler has that auto ... structure binding, it probably is a C++ 26 implementation that may have reflection anyway. So
Fine.
This is only for those of us who won't get reflection in the next few months.
Fine, but even if you don't want to use reflection, you can get at the members of a
Sure.
by structure decomposition.
The more funny question is, how do you do that in 17? You don't have concepts, and it works. I don't have slides for this, but yeah, I can show you how to do it in 17. I'm not sure I can do it in 14 from the top of my head.
I have a curiosity, and because I was out of the room a little bit, I don't know if you covered that, but have you thought how hard would be if I use something like this, then transition to reflection when we get reflection?
I mean, obviously, the only thing where you need any change for this, if you have reflection, is the leaf parts. And if you had a nicer user-friendly API than I just shown with this using declaration, you could just say, okay, my for all members functions now is implemented in terms of reflection instead of all this stuff. So you could do this very locally. And as I said, if you have a user-friendly API, you should probably hide all this ugliness. And then, yeah, it's local changes, no global project changes necessary.
Okay. Any other question? Oh, yeah.
So you're using the Boost preprocessor for this,
Yeah.
and you said that you're using it because you don't want to limit the number of members.
Well, I don't know how many members you need to be supported. And
Right.
There's no correct answer there to give on a general basis, because my default is like something like 10, and then I use this in production and figured, no, it's more like 50. It's an OR mapper, so there's a whole lot of stuff going on there.
Boost preprocessor internally is implemented with a bunch of...
Yeah, but I don't have to write those, right?
Okay, fair.
There's another thing. You probably should only use the Boost preprocessor version if you can use reflection very localized, because actually you don't want this to happen in every file. So either preprocess.file once, or use another external tool. But I wanted to go as far as I can without leaving the C++ preprocessor.
No, just a comment on how limited are you. You would hit the preprocessor recursion limit anyways with Boost or by hand, which is compiler dependent, the recursion limit.
There's probably some lower limit we specify, right?
Yeah, I mean, it's like, I think 65,000 in some compilers. So if you have that amount of members.
I'm going to channel Daniel there. If you have a 65,000 member class.
Yeah.
I don't think this is your problem.
Constructions with Boost preprocessor are limited to 256.
Same statement, 256 sounds like a lot.
This is a limit anyway.
Okay, so it's not unlimited, as you just heard, but if you crash into this boundary, Nobody can help you.
Okay. Any other question? You want coffee? So we go for coffee, and after the break, we will dip into return value optimization.